The European Space Agency released the data from ExoMars camera. They detected the interstellar visitor 3I Atlas that
A bright point, a silvery halo, a tiny smear that still refuses to behave like anything we expect. What you see in that single frame might change how we understand visitors from deep space, or it might force us to look harder at the instruments that made the picture. Either way, it demands an answer. Imagine a camera on a Mars orbiter. It stares into the dark above the red plains for a few seconds. Each exposure is dirt simple. 5 seconds, a star field, a faint dot. Dozens of those frames are stacked. The dot sharpens. The dot grows just enough to look different from a star. No long streaming tail stretches away into space. Instead, a faint glow seems to aim, strangely, toward the sun. The mainstream view is tidy. Comets are ice and dust. The sun warms them. Ice sublimates. Gas and dust stream away. Radiation pressure and the solar wind push debris anti-solar away from the sun. A comet's tail is a faithful weather vane. It always points outward. That rule is so basic it is taught in classrooms and printed in textbooks. Now, meet the anomaly. This object, called 3 Atlas, arrived in our system in mid-2025. It is interstellar. It travels faster than the sun can bind. Its path is hyperbolic, but its route is odd. It came almost along the ecliptic, the flat plane of the planets, not from high above like most interstellar visitors. It threaded past Mars in early October 2025, then bent toward Jupiter. For many, that choreography was the first eyebrow raise. A quick list of hard facts, discovered mid-2025, observed by telescopes on the ground and in space. JWST, Hubble, Keck, Gemini, Keck IFU teams, NASA's infrared facilities, and Mars orbiters pointed at it. Multiple independent instruments, multiple nights. The object is fast. Estimates peg its speed at roughly 130,000 miles per hour. That is tens of kilometers a second. It is big too. Thermal fits and imaging suggest a nucleus measured in miles rather than meters. One team likened it to a 3-mile core that is large for an interstellar visitor. And then the images leaked. That's the phrase people used. Not released, not published, leaked. A stack of frames from a Mars orbiter, cleaned and combined, showed a compact bright core and a faint glow that didn't align with the textbook picture. No long anti-solar tail. A sunward glow. A compact coma. Researchers checked their steps. They median stacked to suppress cosmic rays. They applied bias, dark, and flat corrections to kill instrument quirks. They matched the frames to astrometric stars. The stars stayed pinpricks. The visitors showed a subtle spread, twice the width of a star's point spread. The team flagged that as real. Some instruments barely saw it at all. Mars Express, with shorter exposures and different cameras, registered nothing beyond noise. Other ground telescopes reported faint but consistent spectroscopic lines. Keck's IFU teams called out emissions not commonly seen in cometary comas. JWST's NIR spectroscopy found more CO2 than water relative to expectations. One measured the CO2 to H2O ratio at about 0.57, almost double what many comets show. Polarimetry suggested strange dust. The coma's negative polarization minimum was deeper than usual, hinting at porous, dark grains mixed with ice. Then there were metal lines. Some teams reported clear nickel emission lines, sharp, narrow, unmistakable, they said. But iron, normally abundant and bright in comet spectra, seemed absent or below detection thresholds. In typical comets, iron outshines nickel by orders of magnitude. Here, that ratio flipped. If true, that alone changes the chemistry story. Pause. The mainstream interpretation remains. Many astronomers urge caution. Instrumental effects can mimic lines. Stacking and processing can produce odd halos. Telluric contamination, sky subtraction, cosmic rays, and unlucky coincidences can create spurious signatures. Teams repeatedly check calibrations. They compare against known artifacts. They run Monte Carlo tests. The null hypothesis, that this is a natural comet behaving oddly, is still the default for most. But this is where the mystery tightens. The object's trajectory is not just unusual in angle. It peers along the ecliptic. It passes between planetary giants in a way that looks suspiciously like a gravity assist plan. Gravity assists are how we send probes far and fast. Spacecraft engineers design them. For a random interstellar rock to align with planets in quick succession is unlikely. Some modelers estimate the probability as very low. Others say rare events do happen. The difference is whether rare is a satisfying answer. Consider the physics of tails. Sunlight exerts pressure. Tiny dust grains feel it most. The dust tail fans out. The gas tail, driven by solar-wind interactions and ionized molecules, forms a thinner streamer. Both point roughly away from the sun. So what would make material stream toward the sun? A handful of possibilities exist. Large grains, particles big enough that solar radiation pressure has little effect. They fall into ballistic paths close to the nucleus. In images, these can appear as a more compact haze. Directed jets. If the nucleus vents in a preferred direction, possibly because of rotation or localized activity, a jet could aim sunward temporarily. Charge effects and magnetic interactions in extreme circumstances might redirect ionized gas. Or the simplest and often most resilient explanation, a processing artifact. Only repeated independent observations settle which is real. The spectroscopy deepens the puzzle. CO2 outgassing in such strength suggests a body formed in a different thermal environment. In the cold outskirts of another star system, volatiles like CO2 can concentrate. If that's true, 3I Atlas could be a pristine remnant from a distant disk. That explains some chemical oddities, but not the metals. Nickel without iron is not trivial noise. In our solar system, iron tends to dominate metal emission. Nickel lines standing alone suggest three broad options. 1. The nickel is genuinely overabundant. Maybe the body formed in a metal-rich pocket where iron was sequestered into large grains or compounds that don't vaporize easily. 2. Iron is locked in refractory minerals or in grains too large to sublimate and so escape detection. 3. The nickel signature is misidentified or contaminated by telluric or instrumental features. Teams are chasing these possibilities right now. Polarimetry adds texture. Light has orientation. Dust grains polarize light differently based on size, shape, and composition. This comet's polarization curve points to very porous magnesium silicate grains mixed with ice, dark, fluffy, more complex than textbook dust. That aligns with a picture of a dense, ancient body fragmented into a layer of porous detritus. Or it hints at something else. Size and survival are another riddle. Deep space is harsh. Cosmic rays and micrometeorites grind down small bodies over eons. For an object to remain intact and miles wide suggests either it was recently ejected or it is unusually robust. Thermal models based on Hubble, JWST, and Mars orbiter data suggest a nucleus scope that would rival the largest comets known. Survival at that scale is odd but not impossible. But survival plus odd chemistry and an ecliptic path is what brings some minds to the edge of speculation. Voices of caution and curiosity appear in tandem. Extraordinary claims demand extraordinary evidence, many say. That is the scientific baseline. Yet a few public voices are more provocative. A Harvard astrophysicist who has long advocated open consideration of non-natural explanations recently described the accumulation of anomalies as warranting a higher prior for artificiality. He framed it as an invitation to test, not a conclusion. When many independent oddities pile up, he said in public remarks, we should keep our minds open. That measured tone has inflamed social media and stoked headlines, but it also pushed agencies to coordinate. Coordination is precisely the problem. The best cameras are not always free. Scheduling telescopes takes time. Data release protocols vary. High-resolution images from Mars orbiters, the ones that could settle the nucleus structure, face delays. Some delays were technical, some were administrative. An unexpected government funding pause slowed processing on a few missions. High-rise frames, if taken, were routed through backlogs. That silence created a vacuum. In that vacuum, rumors and doctored images spread fast. Leaks filled the gap. A few processed stacks circulated without full calibration data ignited speculation. Social feeds rewound frames into conspiracies. Professionals pushed back and asked for patience. The core lesson: when raw frames and calibration products stay locked behind team doors, interpretation slips toward rumor. Science needs transparency. The science community has been calling for faster, clearer protocols for interstellar visitor responses. A proposal is now on the table for her automatic data sharing and rapid cross-agency observation. The stakes are high and the clock is short. Let's step back to the nuts and bolts of the data processing. Median stacking removes outliers by taking the middle pixel value across a set. It is great for removing cosmic rays. Alignment on predicted motion sharpens faint moving objects. Calibration files, bias, dark, flat, correct for detector quirks and uneven illumination. Teams cross-compare with astrometric stars to check the spacecraft's attitude. That count of checks matters. When every step is validated, anomalies gain weight. When any step is uncertain, the anomaly returns to suspect status. Astrometry, precise position tracking, is also a tool to decode intent. If the object shows non-gravitational accelerations, that points to outgassing jets. Those produce tiny thrusts that nudge an orbit measurably over time. If the path is consistent with gravitational forces alone, we have one story. If not, and those deviations remain after accounting for cometary outgassing, the conversation changes profoundly. Thermal mapping is another vital test. An infrared map detects heat. A natural nucleus will show thermal gradients driven by sunlight and material flow. An engineered object with internal heat sources would show different signatures. Imagine a warm patch that makes no sense under sunlight alone. That would be an eyebrow raiser. Instruments like JWST and ground IR telescopes can do that work. So can instruments on Mars orbiters in certain bands. Those observations are on the priority lists. What about signals? Radio telescopes can scan for narrowband transmissions. The prior probability of finding an active beacon is low. But the cost of running a few coordinated radio scans is small compared to the question's weight. SETI teams have already suggested simple, targeted searches. Non-detections do not settle the question either way. Silence is not proof. Scientists have sketched a checklist of decisive observations. High-resolution imaging to resolve surface structure. UV and high-resolution near-IR spectra to pin down metal lines, isotopic ratios, and molecular abundances. Polarimetry across more phase angles to refine dust models. Precision astrometry to reveal non-gravitational forces. Thermal maps to test for internal heat signatures. Radio searches for narrowband artificial carriers. Each item, if executed, narrows the range of plausible explanations. Historically, science has seen similar puzzles. The wow signal in radio astronomy produced weeks of frenzy and years of follow-up with no repeat. Tunguska generated immediate rumor and decades of careful fieldwork and explanation. The lesson? Initial anomalies often contract toward natural explanations with better data. Sometimes they do not. Either outcome teaches us something. It sharpens method. It forces new instruments and new cooperation. Why would the object point a glow toward the sun? If it were a relic or probe, one might imagine reflective panels, active illumination, or even a power system projecting light. That is speculation layered on speculation, yet it is a testable speculation. A self-illuminating object would show a power signature. It would have a thermal fingerprint. It may produce narrowband emissions beyond thermal noise. Those are measurable. The beauty and difficulty of science is turning speculative ideas into precise, falsifiable tests. Social dynamics complicate the science. When high-profile voices suggest non-natural possibilities, the public latches on. Social feeds accelerate rumors. Amateur astronomers sift the sky for confirmation. Backyard observers post stacked images from old cameras. The internet turns every feed into evidence and every absence into proof of suppression. That is the modern background noise. Scientists now must manage not only telescopes, but also public expectations. So what would it take to shift consensus? A few clear things. Independent confirmation of the nickel lines from multiple instruments with clean calibrations. A persistent CO2-H2O ratio, reproducible across datasets. High-resolution images resolving the nucleus and showing structure inconsistent with an icy rubble pile. Astrometric evidence for accelerations inconsistent with simple outgassing, thermal anomalies that cannot be explained by solar heating. Put together, such a stack would push the null hypothesis aside. Until then, mainstream caution prevails. Some researchers, however, are not silent. We can't ignore the pattern, one scientist paraphrased in early statements. Multiple strands point to a body that isn't a run-of-the-mill comet. That phrasing is careful. It invites tests. It does not claim discovery. It does not leap. It merely asks more telescopes to look. There are also mundane counterpoints. Cometary science has surprises. Outbursts, spin-driven jets, unusual grain size distributions, and exotic formation histories can produce odd signatures. Carbonaceous chondrites and certain primitive meteorite classes show unexpected chemistry in laboratory analogs. A body formed in a cold, CO2-rich pocket could match some spectral lines. Iron hidden in large refractory grains could explain its apparent absence. Each natural story maps to a set of predictions that teams are racing to test. Operational realities matter. Telescopes cannot all point at once. Observing time is scarce. Instruments on Mars were set to other tasks weeks or months in advance. Data require processing. Calibration takes time. During that time, people rush to interpret partial products. The call for rapid data sharing is not new. It is urgent now. Agencies and committees have begun drafting a rapid response framework. The idea: when an interstellar visitor arrives, teams worldwide agree to share raw frames, calibration files, and initial reductions fast. That would reduce rumor and accelerate measurement. What about human stories? Picture the lab at dawn. A grad student on coffee checks a stack. She sees the spread widen. Her phone pings with a director's note. Conference calls start. Instrument teams gather. The tension is real. Scientists are human. They carry professional caution and genuine excitement. They know that a misstep can mislead millions. They also know that missed opportunities are permanent. Those human stakes shape the rigor. Backyard observers add texture. Amateur stacks of pre-discovery images feed the timeline. TESS pre-covery stacks, for instance, can extend the light curve months earlier. Those contributions are invaluable. They help locate when activity began. The public becomes part of the data set. That changes outreach too. Clear, simple messaging matters. Scientists now write for professional journals and public feeds. Both audiences matter. So what are the plausible headline scenarios, short and crisp? 1. Natural comet with unusual composition and grain properties. 2. A relic of unusual origin, a natural body formed under strange conditions. 3. An engineered object, a probe or relic, with detectable non-natural signatures. The order reflects prior probability. The evidence currently fits the first two more comfortably. The third remains low prior but not untestable. If the engineered hypothesis were true, the consequences would be profound. We would face immediate questions about purpose and origin. Was it a probe? A beacon? A derelict vessel? The ethical and political weight would be heavy. Nations would call for coordination. The United Nations Committee on the Peaceful Uses of Outer Space would convene. International protocols would be discussed. The stakes would be global. That is why scientists insist on extraordinary evidence. If the natural explanation holds, the payoff is still huge. We would learn about planetary formation, about exotic chemistry, about how objects survive interstellar travel. Each new comet expands our textbook. Even a rare, pristine body teaches us about the diversity of planetary systems in our galaxy. What will we see next? The object will move on. Perihelion near the end of October 2025 hid some observations behind solar glare. That window was a blind spot. After perihelion, the object will head outward. It will pass by giant planets. Each encounter is an opportunity to watch gravity and material interact. Each telescope we point now collects data we cannot recover later. The final, simple truth: evidence will decide. The instruments will talk. Stacks, spectra, polarimetry, and astrometry will converge. Some anomalies will fade under rigorous checks. Some will persist. We must let the data speak. For now, we stand at the cusp, a bright dot in a stacked frame, a halo pointing where it shouldn't, lines in a spectrum that refuse easy explanation, human beings arguing in conference rooms, backyards buzzing with amateur stacks, agencies drafting rapid response rules. The drama feels cinematic. The method remains scientific. So what should you watch for? High-resolution images that resolve the nucleus, independent spectroscopic confirmations of nickel and the CO2 ratio, polarimetry across more phase angles, astrometric measures of tiny accelerations, any thermal anomaly that cannot be solar in origin, simple tests, clear outcomes. And if you want a question to carry with you, what would you do if one image suggested a technology designed outside our understanding? How would the world balance skepticism and the hunger to know? How would scientists guard against error while still moving fast enough to catch a fleeting signal? We will know more soon. Telescopes are pointed. Teams are working through calibration files. Data that were once siloed will likely see daylight. With luck, the next release will close some doors and open others. Until then, the image is both a promise and a provocation. Keep your eyes on the sky. Watch how the data arrive. Listen for the quiet, cautious language of scientists as they test, cross-check, and repeat. This is how discoveries become facts, slowly, insistently, and with a stubborn humility that real mystery demands. One frame, one glow, one anomaly. Is it a comet that rewrites a manual or a visitor that rewrites our questions? The next image will tell us more. What will it reveal?